And now we're going to make an electromagnet. This is a magnet that we can turn on and off with electricity. Our electricity will come from a battery, and this is what our electromagnet will look like. It is a single bolt, and we're going to pretend like that wire is not on there right now. And just note that that bolt is not magnetic. If you get one that's already magnetic, that will defeat the purpose of turning magnetism on and off. So as we add electricity to the wire wrapped around it, notice this is an insulated wire. The edges need to show the copper, so you may have to take wire strippers and to cut that off. As we add the battery, one end touches the negative end of the battery, one end of the wire touches the positive, and now we have a magnet. If we turn off the electricity, now the magnetism's turned off as well. You can see how this could help you in real life. For instance, at a junkyard, sometimes you may have seen a giant electromagnet actually pick up a car, move it, and then drop the car. That's just magnetism being turned on and then turned off. It's an electromagnet. Right now we have a compass on the table and it's pointing north, but we're going to overcome the Earth's magnetic field by generating our own magnetic field that's even stronger, simply using a battery, aluminum foil wire, and our compass. I've taped our wire to the table so it doesn't wiggle around. You want to align the compass needle with the aluminum foil so that you can see the starting point. But then, as you add a battery, you can see the needle points in a different direction. If I flip the battery around, we change the polarity, and the needle turns in a different direction. We've simply made a magnetic field stronger than that of the Earth. It overpowered the compass, and we could flip that magnetic field back and forth by changing the direction of the electron flow. And now for one of the most remarkable demonstrations of how electricity and magnetism work together. This is called Lenz's law, and we're just going to simply watch a demonstration and try to figure it out. All we need is a copper piece of tubing. It's hollow inside, and notice that copper is not magnetic. Even though it's metal, it will not attract this paper clip. When we drop this green bead into the copper tubing, it travels through almost instantaneously just due to gravity. These are permanent magnets. They have a permanent magnetic field. But as I drop them down the copper tubing, there's an induced magnetic field in the tube that pushes against the permanent magnets, causing them to slow down. With this demonstration of Lenz's law, what we see is that as we drop the magnet down the copper tube, as the magnet moves, it generates or induces electricity or an electrical current in the copper, which in turn has its own magnetic field associated with it. That magnetic field pushes against the magnetic field of these magnets as it drops and slows the drop considerably.